Today we're going to talk about exponential equations. As we're going through this section, just like every other section in Chapter 4, we're going to use our domain or our universal set as the set of real numbers. Right, so up at the top of this page we have our definition for an exponential equation. The big difference between what we have seen so far and exponential equations is where our variable is. So an exponential equation is an equation of the form a to some expression is equal to b, where a is a positive real number other than 1, and the expression is a math expression containing the variable. Right, so as we're thinking about our definition, the big difference between what we've seen so far, we've definitely seen questions that have exponents in them, but those questions that we've seen, those exponents have been numbers. In this case, when we're dealing with exponential equations, our exponents are going to be containing variables. At the bottom of this page, this is just kind of a reference sheet, so that way as you're going through and working on these problems, it has some common perfect powers. So it has our perfect squares listed through 12 squared, cubes, some fourth powers, and some fifth powers. Not that you can't generate some of these numbers on your own as you're going through the problems, it just might be handy to keep this sheet next to you as you're working through a couple of our examples, and we'll kind of talk about that as we go through these. All right, so our first example here is asking us to identify our equation types, right, and then solve if possible. Right, so looking at our first equation that we have is x squared equals 9. This particular equation is an example of a quadratic equation, right, because quadratic equations we've seen in the last few chapters, that's when we have something that is squared. We could solve this a few different ways. We could move the 9 to the other side and then factor as a difference of squares. We could square root both sides using our square root property that we talked about in section 4.3. I don't necessarily know that we would want to try to use our quadratic formula for this, but if we were to either factor it or square root both sides, we get x is either a positive or negative 3. Right? So our solution set would contain both a positive 3 and a negative 3. Right, now if we compare this to example B, in example B we have the 3, right, but what we're missing is our exponent. Right? So in this case, since our variable is in the exponent, this is an example of an exponential equation. Right? And this is asking us what power of 3 gives us 9. Right? And we know that if we square 3, if we take 3 times 3, we get 9. So in that case, our power on this 3 has to be 2. Right? So we have one solution here, and our answer is 2. C is also an exponential equation. Right? But looking at this is asking us 2 to what power equals 9. Right? If we go back to our little table here, and we look across our row of 2's, well, 2 squared is 4, 2 cubed is 8, so that's close, right? But it's not equal to 9. 2 to the 4th is 16. So we don't have a power of 2 that exactly is equal to 9. So looking at this one is not answerable yet. Right? So our goal in this section is to come up with a way to solve these. Right, so we're going to have two main types of problems that we're going to see as we're going through the section. Our first problem is going to be very, very similar to example B. We're going to have an exponential equation, and then we're going to generate a variable, or the number that is going to replace the variable, to figure out our perfect power. So in this next example, we're going to be using something called the exponent rule of equality. So if we have the same base, so if we have the same number on both sides raised to two different expressions, then those two expressions that we have to be equal to one another. So as we're going through and working out these problems, we're first going to think about, well, what power of our number is going to give us the desired result on the other side of our equation, and then once we have that number, how can we use that to solve our equation? All right, so looking at example A, right, what we're going to do is we're going to start by figuring out what power of 4 is equal to 16. Right? And we're going to rewrite our equation as 4 to the x equals And if we think about 16, 16 is 4 times 4, so 16 is 4 squared. So 4 to the x is going to be equal to 4 squared. Right, now if we look at these, what our exponent rule of equality says is basically if these two bases are the same, which these are both 4s, we can basically just kind of cancel them out. Right? What we're going to focus on is just their exponents, which then have to be equal. So that's going to tell us that x has to be equal to 2. Right, so this is the same thing that we used up in example 1b when we solved 3 to the x equals 9. Right? If we have a number that's a perfect square, our exponent that's missing is going to be a 2. All right, in example B, we're going to start by doing the same thing. Right, so we're going to have 2 to the x plus 1 equals, and we need to figure out what power of 2 is 32. Right? So that's one of the reasons that I gave you guys this handy dandy table. So looking at our powers of 2, 2 squared is 4, 2 cubed is 8, 2 fourths is 16, 2 to the 5th is equal to 32. So we're going to replace our 32 in our problem with this 2 to the 5th power. So 2 to the x plus 1 is now equal to 2 to the 5th. That means, again, we're going to not consider our bases since our bases are the same. We're just going to focus on our exponents and set those expressions equal to one another. So we have x plus 1 is equal to 2. If we subtract 1 from both sides, then we get x is equal to 1. So our final answer for this one is going to be 1. Right. C, we're going to set up the same way. So 5 to the square root of x equals 5, and we have to figure out what power of 5 is 125. 5 squared is 25. If we multiply that by 5 again, we get 125, so 125 is 5 cubed. Again, you can either generate it kind of talking through it or looking at it, or we can go back to our table. We see that 5 cubed is 125. Right. Then again, we're going to focus on our exponents here. Right. Set those equal to one another. So our square root of x is equal to 3. A square root equation, remember we square both sides to get our answer. So we square the square root of x, we simply get x. We square 3, we get 9. Okay. All right, so all three of these examples, again, as we were going through, we were using our exponential rule of equality. Right? What that means is this number on the left side is raised to some power that's always going to be equal to that number on the other side. Right? If we go back and look at our previous example, right, again, we could solve B using that property, right, but we could not solve C. So our goal for these next few examples is going to be to come up with a way to solve an equation like C, where it's not necessarily something that matches up perfectly as far as the power of our numbers. All right, before we can do that, we need to define something called a logarithm. So up at the top here, we have a list of some different facts about our logarithms. Right? So our base of our logarithm is the same as the base of an exponential equation. We're going to be focusing on base 10 logarithms. So that's what number 2 says. Number 3 is going to give us kind of a way that we're going to solve our first few equations. We have this notation, this log base 10 of a is equal to x is the same as 10 to the x equals a. And then the fourth thing, it says that all scientific calculators have a log key. So scientific calculators, graphing calculators, even the scientific calculator on your phone has a log button. If you're looking at a basic TI-30, like we used a lot in class, and that I mentioned a lot in class, our log button is right up here at the top. So as you're going through and you're working through these, if you have a scientific calculator handy, or even a scientific calculator on your phone, you should have a log button on there. All right, so example 3, we're asked to evaluate the following logarithms without using a calculator. Right, so what we're going to be asked to use here is we're being asked to use this property. Right? So this is telling us that as we're looking at these, the number that we get on the other side is the same thing as our power would be for our 10. So if we look at example A, right, what we're thinking about is the log base 10 of 10, right? And then we're looking for this missing number here, right? Is the same as 10 to that missing number equals what we have on the other, what we have in our parentheses, which is our 10. So if we look at this, right, 10 to what power equals 10? That's basically the question that we're answering. Well, 10 to the first equals 10. So our log base 10 of 10 is equal to 1. All right, for B, right, we're thinking the log base 10 of 1,000, right, is the same as 10 to what power equals 1,000, right? 10 times 10 is 100, so 10 squared is 100. 10 times 10 times 10 is 1,000, so this is the same as 10 to the third. So our log of 1,000 is going to be equal to 3. Right. Our log base 10 of 100,000, right, is the same as 10 to what power equals 100,000. When we're dealing with powers of 10, remember a power of 10 also refers to a number of zeros, right? So 10 to the first has 1 0, 10 cubed has 3 zeros, so that was our 1,000. If we count our number of zeros here, we get 5. So 10 to the fifth is 100,000. That means our log of 100,000 is equal to 5. So if we're dealing with powers of 10, you don't necessarily have to kind of write out or go through this whole process on the right. Basically, if we're dealing with powers of 10, then we're just going to be counting the number of zeros, right? We're trying to figure out what power of 10 gives us this number that's in our parentheses. Right, now if we look at the example at the bottom, well, the only problem is here, right, these are not powers of 10, right? There's nothing that we can think of off the top of our head, right, to raise something to get a power of 10. So this is where you're going to want your scientific calculator, right? So as we're going through these next problems, we're going to use our calculator to help us answer them, right? So if it's not a perfect power of 10, you will require a calculator to do these problems, right? So our log of 3, right, for the most part, we're going to round these to 2 decimal places. So our log of 3 is going to be 0.48. Our log of 12 is 1.08. Our log of 145 is 2.16. And as we're looking at these, we are going to see decimals for these answers. Anything that's less than 10, we're going to get 0 point something because it's a less than 10 to the first. Anything between 10 and 100, we're going to get 1 point something because it's a little more than 10 to the first, but a little less than 10 squared. Anything between 100 and 1,000, we're going to get 2 point something. So as we're looking at these, our numbers in here are going to go up quickly, but our numbers over here on the right are going to be smaller decimals because we're thinking about powers of 10. Right. So for D, we're going to do the log of -3. Notice that we get a domain error here. Right? We cannot take the log of negative numbers because there is no way to turn a positive 10 into any sort of negative number using exponents. Right? So in this case, we're just going to say that we cannot answer that. So anytime we have a negative number, we cannot find the log of a negative number. Right? We can, however, take the log of decimals. So our log of 0.5 is going to be -0.30. If we're taking the log of decimals, notice that we're going to get negative numbers for a result. Right? And our log of 0.01 is going to be equal to -2. Right? Technically, this is 10 to the -2 power. So if we're getting decimals in here, negative exponents represent decimals or fractions. So if we're taking log of decimal numbers, we're going to get negatives for our values over here. All right, so now that we've talked a little bit about our logarithms and how we can find them using our calculator, we're going to use logarithms to solve our equations. So looking at example A and example B, we already solved this using our exponent rule of equality because we know that 3 squared is equal to 9. So we should expect when we solve this one that we're going to get an answer of 2. But notice B, we said earlier that we were not able to solve that yet. So as we're going through and we're thinking about this, we're really focusing on problems like B and C that we would not be able to solve without using logarithms. All right, so our steps up at the top, or our useful properties, I should say, it's not necessarily our steps, but our useful properties. If we have two expressions, the logs of those expressions are going to be equivalent. So as we're working through these, our first step is going to be actually to take our log of each side. And then our power property of logarithms say that whatever our exponent is, we can bring out front. And that's going to be the second step that we're going to use as we're going through all of these different equations. Okay. All right, so to solve example A, we're going to use that first property up at the top, and we're going to take our log of each side. So our log of 3 to the x is equal to our log of 9. Then our second property says whatever our exponent is up top, we can bring out front. So I'm going to rewrite this as x times our log of 3 is equal to our log of 9. So our exponent that was up top, our power that was up top, drops down out front. Right, now we want to get x all by itself. Right? If we want to get x all by itself, that means that we need to get rid of this log of 3. Right now that's being multiplied by x. So to get rid of that, we're going to divide both sides by the log of 3. And that's going to give us that x is equal to the log of 9 divided by the log of 3. So now we can go to our calculator and we can plug this in. So I'm going to do log of 9. You do want to make sure that you close off those parentheses before you put the next number in. Divided by our log of 3. Log of 9 divided by log of 3 gives us the number 2. So no decimals here. X is equal to 2. For these problems, if you're asked to write both your answer as an exact answer and as a decimal, if it works out perfectly, then they're the same. So in this case, our final part here is we're going to write out our answers. So our exact answer, right, is equal to 2, and our rounded answer, or our decimal equivalent, is also equal to 2. All right, so example A, again, we could also solve using our power of equality, and our answer that we got matches what we saw previously. Right, for B, right, this is the one that we said before we couldn't solve. We don't know a power of 2 that's exactly equal to 9. We know that 2 cubed is about equal to, or is equal to 8, but we can't raise a power of 2 and get a 9. So we're going to start this the same way. Right? We're going to take our log of each side. So our log of 2 to the x is equal to our log of 9. Then we're going to use our other property, and we're going to bring our exponent down out front. Right? Then just like we did in the previous example, we're going to divide both sides by our log that's next to our x, so that cancels. Right? And we are left with x equals the log of 9 divided by the log of 2. This part using our logarithms, in this case when we divide these, we are going to get a decimal. So we're going to do the log of 9 divided by the log of 2. We get 3.169, which is going to round up to 3.17. So we're going to say this is approximately equal to, so we're going to use a little squiggly equal signs, 3.17. In this case, all right, our exact answer, we're going to leave it in logarithm form since we get a decimal. So our exact answer is going to be log of 9 divided by log of 2. Right? And our rounded decimal approximation, right, is going to be 3.17. Then lastly, example C, we're going to set up the same way. So we're going to start by taking the log of each side. So the log of 5 to the x plus 2 equals the log of 10. Right, our exponent is going to move down out front. This time our exponent is not just a plain x, it's an x plus 2, but that's okay. So we're going to put our whole x plus 2 out front times our log of 5 equals our log of 10. And just like we did in the last couple of examples, we want to get this x all by itself, but before we do anything, we're going to divide both sides by our log that's on this side to move that to the other side. So we're going to divide both sides by the log of 5. So now we have the x plus 2 is equal to the log of 10 divided by the log of 5. Okay. Now thinking about this being any other normal equation, right, if we had x plus 2 equals 5, well, we would finish that off by just subtracting 2 from each side. So that's exactly what we're going to do here. We're going to subtract 2 from each side to get x all by itself. So that is going to give us that x is equal to the log of 10 divided by the log of 5 minus 2. So when we plug this into our calculator, we're going to take the log of 10 divided by the log of 5. We're going to go ahead and equal that out to get a decimal, and then we're going to subtract 2. Okay. We get negative 0.569, so that's going to round off to approximately negative 0.57. Right, so here our exact answer is going to be our expression using our logarithms. Right, so log of 10 divided by log of 5 minus 2. And then our rounded approximation is the negative 0.57. So as you're working through the problems in this section, kind of pay attention. Is it something that works out perfectly, or are you told to use your power rule of, or exponent rule of equality when we know something works out nicely, like it did in example A, or if it's something that we don't have a perfect power that works out, we can use our logarithms to solve those.